still Monday, February 10th. This is still CS 746. And today we're talking about, or now we're going to talk about examples of hypothesis testing. So just a couple of examples we put together, just kind of demonstrate how it works, because it's not enough just to say, this is it. We need to, get some feel for it, right? So yeah, we know where we're at. In the z-test example, so we have some university, wherever state university we'll call it, and the average age of students at this university has historically been 23.0 years old with a standard deviation of 2.4 years. So this semester we went out, we found 42 students, and we asked them how old they were. And they said, they gave us their ages, and we averaged that up, and we got an average of 23.8 years. So our population has historically been 23 with a standard deviation of 2.4. Our sample is 23.8, right? But we don't have the, we don't even need the variance on this, right? So we're going to use a z or a t-test to find out if this is a significant difference. Right? H naught, this is the age, 23.0. H1, the age is not 23.0. Again, in this case, our population variance is known. The standard deviation is just the square root of the variance. And our sample size is bigger than 30. So that's 2 strikes against the t-test. We're going to use a z-test. Right? And if you want to watch this, I built this off a YouTube video that you come back and watch too. Set the hypotheses, H0 and H1. H0, nothing's changed. Nothing interesting's happened. H1, something has changed. We set our significance level, we compute the test statistics, we make a decision. Hypotheses, we're going to use a two-tailed test. The mean age this semester is not 23.0 years. We're looking for if it's on the high end or the low end. Did it grow significantly? Did it shrink significantly? We set our significance level. For this example, we're going to try 2 different confidence or levels. We're going to try an alpha 0.05. We're going to try an alpha 0.02, or a 98% confidence interval. And we'll see that we get different answers. In this case, why? Because the p-value is between those 2 numbers, right? So we're testing for not equals. Therefore, we want a two-tailed test. This means 0.025 on either side. So we go to our Z table, which I forgot to upload. Okay, and so we go out to the web, and we get that out of the way. By the way, it's easy to find these things. Well, maybe it's easy. There we go. University of Florida, that sounds good. There we go. This is a standard Z table. We'll download that. We'll go to downloads. Doesn't know how to open it. Jeez. Wow. Okay, fine. Okay, so here's a Z table looks like. This is a typical Z table. No. Here's the. Okay, what's next? Okay, here's how this works. I got a whole picture here. Here's the value, our Z value, right? We're going to find our Z value that we calculated. What level of confidence do we want? So our cumulative probability for Z is the area under the standard normal curve to the left of Z, right? So for instance, if I get a Z value of minus 3.49 and combine the row and the column, right, we only have a 0.002% chance of it being less than that. If we get down to a Z value of 0.00, you see that's the right in the middle of the curve. Half the data is less than that, half is bigger than that, right? So we come back to our question here. We find 0.250 in the Z table. So I go 0.250. We're looking in the middle here. 0.250 0.0250. 0.0250. And there it is right there. Okay. Now we find out what is the z statistic that gave us that probability. And we read over here, we see it's minus 1.9. And we go up here, 6. Minus 1.96. We'd already seen that on our lecture before. That is, a z statistic. So again, that is 2.5%. Okay. We read that to 3 decimal places using the row and column heads. We get 1.96. It's negative, which means we're on the left side, but it's the same thing on the right side as well. So that tells us the likelihood that we're out in those tails, right? If we look at a 98% confidence level now. Oh yeah, there. Yeah, okay. I have the slide already downloaded there in the presentation. I've got circled there. Now we set our significance level. So we're going to try our 2 different ones, 95 and 98. And 0.01 out of the tail, we find the z table. For 98% is 0.0102. If we look in our t table, in our z table here now, we don't have a 0.01 in here. We have a 0.102. And 0.099. So we have to interpolate. So 100 is 1/3 of the way from 2.32 to 2.33 to 2.32. So we go 2.326 is what we look for. And you can also get a smart calculator just up in there too, right? So, or just the computer, why make it so hard? Yeah, there we go. And again, there we've interpolated. Now I compute our test statistic. We're already using the z-test. So we have x bar minus mu over sigma. 23.8 minus 23 over 2.4 is 0.33. That is our test statistic as a single observation, though. Is that the right formula? No. What we have is we have a mean. We have multiple samples. So we have to actually use a different statistic. And this is z statistic is the mean we calculated minus the original mean divided by sigma, and that in turn divided by the square root of the sample size, because we have a bunch of samples. And now we get a statistic of 2.16. And this is the statistic we're going to compare against our alpha value. 2.16 is more extreme than 1.96, so we reject H0 at the 95% confidence interval. For the 98% confidence interval, it is not more extreme than 2.326. So we do not reject the null hypothesis. We accept it. We conclude we do not have enough evidence to be 98% sure the mean student age has changed, right? T-test example. This semester, we don't know what the standard deviation is. We only asked 12 students. We got a standard deviation of 2.4 years in our sample. Right? We don't know what the overall is, right? In this case, we don't know the standard deviation of the population. Our sample size is less than 30. We're going to use a t-test. The hypotheses are unchanged. Significance level, we'll use the same thing. We're going to look in what's called a t-table now. The t-table looks different. We're going to look in the T9.975 column. We've got 12 samples. That means 12 minus 1 is 11 degrees of freedom. So we look at our table, we're going to say our critical value is 2.201. Here we go. We want T.975, this column right here. We look for our degrees of freedom of 11. We find 2.201. This table is kind of inverted from the Z table, right? This is how many standard deviations we are away from the mean. We compute the test statistic. Here's our formula for the test statistic. We're going to get 1.153. 1.153 is not more extreme than 2.201. We conclude we do not have enough evidence to reject the null hypothesis. We conclude the student age has probably not changed. We don't have evidence to show that, right? We're not even going to bother doing 98% now. Right? And that is our hypothesis testing example. 1142, 1215. Yes, we're great. We're great shape. Okay. I need that. Now we're going to do our third recording